Hello and welcome back for another Pytorch video. So I got a pretty cool video for you today. TensorBoard has some pretty cool stuff that we're going to go through. But first of all, we need to actually be able to install TensorBoard. So what I did is I have Pytorch 1.4.0 and I installed the latest preview version of TensorBoard, which is pip install tb nightly. So if you got any difficulty using TensorBoard or installing it, I suggest trying those two out, especially if you're on Windows. But so now that we got that covered, let's actually go to the code. So here I got some pretty basic code. If you don't know how to code a basic CNN or don't understand this code, check out my video on that. We're gonna assume you have some working code and then build TensorBoard on top of that code. And what we're going to start with is we're going to import, first of all, from torch.utils.tensorboard, we're going to import SummaryWriter. Okay. Essentially, this is to print to TensorBoard so that we can visualize it. And yeah, so regarding the code, I just have a very simple convolutional network, which is built for so it's built for in this case, the MNIST dataset, which we just import. We have a data loader, we initialize some hyperparameters, and then we just train the network. So nothing out of the ordinary. The only thing I did at the end here is calculate a running training accuracy. So yeah, just a training accuracy at the end here. And let's see. We want to, first of all, we're gonna define a writer, which we're gonna do SummaryWriter, the one we just imported. We're gonna do an f string. Actually, we're gonna do runs/MNIST, and then let's just do trying out TensorBoard, something like that. So what this says is it's gonna write to the runs folder, which is a subfolder of the folder we're currently at, and then it's gonna write to an MNIST folder and then trying out TensorBoard. Okay, so we've just specified where it's gonna write all the data files that TensorBoard can read. Then at the end of every batch here, what we're gonna do is we're gonna do writer.add scalar, and we're gonna do training loss. We're just gonna start with actually printing the loss as it decreases for each batch, and then we're also gonna do another graph for the training accuracy. We're gonna do training loss, and then what we need to do is we need to add some global step, which we're just gonna call step, and we're gonna define it here. So step is 0, and then we're gonna do step plus equals 1. So when it's added one data point, it's gonna move one more step for the next one. And we're gonna do another thing. We're gonna write add scalar training accuracy, and then so I computed a running training accuracy on the batch. So we can do running train accuracy as float the number of correct for this mini batch, and then float data shape 0, just the number of examples that we send in for just this specific batch. And so that's the value that we're gonna track, and then again global step equals step. Okay, that's the basics. Let's run this and I'll show you how it looks in TensorBoard. So the code has run for a few epochs, and I use Anaconda. If you don't use it, I guess you just use the command line. But essentially, we move to the folder that we're like the model is training at, and then we're gonna do TensorBoard log there, and then runs because that's where that's the default folder name for where we store all of the things related to TensorBoard. But so we run this, and we get back, let's see. So we get back that we're going to look at this link, this URL. And then when we go to that, we see something like this. So this is essentially, this is the loss, which records for each, so the loss for each batch, which explains why it varies, and then the training accuracy. All right, let's do something more interesting now, because we can use that to track hyperparameter search, for example. Let's say we're interested in knowing which batch size and which learning rate match well together. So what we could do is we could define an array, batch sizes, which let's say we're interested in a batch size of 1, 64, 128, and 1024. And let's say we're interested in a couple of different learning rates. Let's say we have 0.1, 0.01, 0.001, and yeah, just another 0. I just want to say that this is not the best method for doing hyperparameter search. You would actually do them in log space and randomized, but for our sake, it's good enough. We just want to learn TensorBoard. So what we're going to do is for batch size in batch sizes, and then for learning rate in learning rate. Then we're going to define all of this stuff. So we're going to run this for each of those. And also one more thing, we need to actually put the train loader. Yeah, we need to put the, I think we need to do that. Yeah, we need to move the train loader because of the batch size. And we need to move the optimizer. Let's actually move the loss as well. I don't think we need to do that, but let's move it anyways. So like this. And then let's also put the writer here. And let's say we do runs. Let's do say mnist, and then we do mini batch size of batch size learning rate, and then let's just put the learning rate. So because we're gonna plot all of these, let's see, we're gonna plot all of those loss functions and all of those accuracy in the same plot. So we want to have some sort of name to actually distinguish them. And let's see, is there anything else? Unexpected idented block. Yeah, one more. This. And that should be enough, I think. One more thing we need to do actually is I need to remove those. So just to not store the last ones that we did. So let's see, like the folder here runs. Let's just remove that folder so it's empty. And I think that should be it. So remember, we're not actually using this learning right now. We could just as well remove it. We're not using this batch size either. And so let's run this, and I'll come back to you when it's all done. So actually, let's just do a few changes. Let's change the number of epochs to 1, and let's just remove the 128 and just have 3 batch sizes. So 1 small, 1 intermediate, and 1 large, and all the different learning rates. And then just one other thing is let's put the network inside here as well, so that we kind of reset the parameters, and also model.train. Yeah, so we changed the number of epochs, just it doesn't take too long to run. All right, I'll get back when this is done. So here we have the plot of the training accuracy and training loss in the TensorBoard. So as we can see, it's kind of many, and we could analyze it like this, but just to make it a little bit simpler, let's do like search for just the batch size of 2, and then we can compare just 4 of those. We can see that, so let's see, we can see that the learning rate of 0.001 and also the smallest learning rate are the 2 best ones. So for a very small batch size, we want quite a low learning rate in this case. Let's change this to, what was it, 64? Yeah. yeah, so we can see that 0.1 is just too large. It doesn't train at all. And 0.001 seems to be the best. The smallest learning rate is not really, yeah, okay, so actually 0.01. So quite a large learning rate is best for this batch size. And 1024, let's see, so now it seems that, again, 0.01 is the best. 0.1 is not that bad, and 0.001 is not that bad either. So the trend that we can see is that smaller batch size seems to correlate with a lower learning rate, which kind of makes sense since we're doing a lot more updates. And when we're computing gradients for a larger batch size, the gradient is more exact, so we can afford having a larger learning rate. That's sort of the interpretation we can have. But one thing that is a little bit problematic is that, so the plot it's kind of not that nice to look at. We can make it better, as we did, like searching just for specific ones. But I'm going to show you another way of having these hyperparameters to make it a little bit easier to look at. So what we're going to do is we're going to go back to the code, and we're going to, let's see here. We're going to first, so I store, let's see, the accuracies is just an empty array. We're actually going to add accuracies dot append run training accuracy. And then we're going to use something to visualize the hyperparameters in a perhaps better way. So we're going to do writer add hparams, and then we're going to do, in a dictionary, we're going to do learning rate, which is just the learning rate, and then batch size, or b size, it's just batch size. And then we're going to do another dictionary. We're going to do accuracy, which is going to be the sum of accuracies divided by the length, so just an average of the accuracies. So this is not an exact accuracy, it's just it's just to get an understanding of how TensorBoard works. You might actually, in practice, you would do this differently, I guess. You would have a getAccurate function and just compute the exact accuracy after that specific epoch. So let's see, what we want to do also is we want to add loss, which is the sum of losses divided by the length of losses. And yeah, actually this should be, so this should be at the end of the epoch. So after we've gone through all the batches. Let's see, is there anything else? I don't think so. So I'm going to run this again, and we're going to see how that plays out differently than how it looked now. So it's finally done training. So as we can see, we have the same plot as we did before, this ugly looking graph that were hard to look at. This hparams is the new one. And first of all, you have sort of a table of all of the accuracies, which might be useful. You can do some metrics here. You can bound the accuracy and do some stuff here. What we're going to look at is the parallel coordinates view, which is pretty cool. I'm just going to make this larger. So let's see here. Okay, so now we can see sort of the loss function, and we can sort of see which accuracy and the batch size and the learning rate that corresponds to. So we can sort of see that the absolute worst you can do is have a small batch size with a very large learning rate. And then if we, for example, look at, so a large batch size with a very small learning rate is bad. Let's see, having a large learning rate with a larger batch size is not ideal in this case, but it's not terrible. It seems to actually do some training. And so we can sort of draw the same conclusion as we did when we looked at the graph, but let's see, for small batch size, let's see, we can see that, okay, very small learning rate is actually very good. One thing you could also do is you can highlight, so let's see if I can do that. We can highlight just a few of those, and we can see sort of, okay, what were the smallest loss values, where did they come from? So the absolute best seems to be, in this case, having a very small batch size with a relatively low learning rate. Let's see what is also good. Also having a little bit larger and learning rate, and then okay, batch intermediate batch size with 64 and a high learning rate is also seems to be quite good. And yeah, 1024 with a relatively larger learning rate also seems okay. Yeah, so this is another way to kind of do the hyperparameter search, and you can play around with this with different things. You can do sort of using different optimizers. You can do different learning rates, different regularization parameter, really whatever you want to have. All right, now let's see. I'm gonna show you another cool thing we want to do, which is, let's say that we're not performing any transformations, but let's say we were performing some transformations to our images, and we want to actually see like how do they look like in our training. And what we can do is we can do image grid is torch vision .utils.make grid of, in this case, data, because data is the images. And then we can do writer.add image MNIST images, and then image grid. And let's also see, okay, so I'm gonna do one more thing, is we're gonna also, let's say we want to see how the weights of our network changes as we train it, which might be useful for some debugging purposes. Let's say that the weights are stuck, so they don't update at all. If we can visualize them some way, we can see that, okay, well, the layers, I mean, the weights in this specific layer is not changing at all. And how we would do that is writer.add histogram, and let's call it FC1. Let's actually look at the last linear layer, so the distribution of the weights for the last linear layer, this one. We could also do it for the com layer, let's just pick the last linear layer for simplicity. And then we'll do model.fc1.weight. Okay, so we're doing two things at the same time here. We're visualizing the images of our specific batch that we're sending in. We're also visualizing the weights of the last linear layer for each batch. And let's not do all of these again, because we already saw how that looked like. And let's pick just a single batch size and a single learner rate, just to make the training a little bit faster. One more thing is that you would actually like to have, so you would like to remove this folder or change, add another folder. It might mess up the graph if you plot again. So let's just remove this one. It's not right. Okay, well, let's see. We have to, I guess, close down the TensorBoard, and then we can remove it, I guess. So let's now run this, and let's start the TensorBoard, and let's see how that looks like. Now there are now it's just a single plot, right? We're just doing for a single one. And now we can see that we have sort of new sections here. We have images. So these are the images for our batch, right? These are, so 8 times 8, 64 images in our specific batch. And also we can sort of trace the images for each batch. Now these just look like MNIST images, but let's say that we would have some transformations. They might look different, and we want to actually see, well, how do they look like? Do they make sense, etc. And then So we're going to look at histograms. So this is pretty cool. Yeah, we want to see this one. So we can sort of see that these are the distribution of the weights, and so we can see that sort of it looks like a normal distribution almost, and sort of pretty small weights. 0.005 seems to be the most common value. Now we can sort of see, most importantly, that the value seems to change as we iterate. If, for example, they would all look the same, and then we would probably say that, okay, well, something's wrong with our model. Can be useful for debugging purposes. So now that we understand those parts of using TensorBoard, let's look at something very, very interesting and cool. Let's try to do some what they call visual embeddings, to kind of visualize how the model does the predictions. First of all, let's just move this writer here to at the bottom, so we can do like plot things to TensorBoard. And what we're gonna do is we're gonna add, first of all, we're gonna add classes, which is gonna be just an array of, might be actually be a dictionary. No, it's gonna be an array, I think. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So those are just the classes we have, right? The digits. And then we're gonna do one thing here. We're gonna let's see where it's best to put it. Let's do it here. Let's call it we call it features, and we're gonna do data.reshape. Data shape 0 minus 1. And then we're gonna do writer dot. We're also gonna do class labels, which is classes, and then label for label in targets. And targets is what is the correct values in this case for the class. And then we're going to add it down here, writer.add embedding, and we're going to do features. And then metadata, we're going to set to class labels. And then the label image is going to be data dot, so we're going to do data dot unsqueeze, and then the dimension, which is 1. I'm going to explain this just quickly. The data that we have now is, so the number of examples, which is 64, and then it's 28 by 28. But the add embeddings expects to have the number of channels here, which in this case is just 1, right? So we're just going to add another dimension here so that it becomes like this: 64, 1, 28, 28. So essentially add one dimension with just a single value in that dimension. That's what this does. And then we're also going to do, global step is going to be equal to batch index. And yeah, we're going to have just a single batch size and learning rate just to make it simple. And yeah, let's see if this works and run it. Okay, add embedding got metadata. Yeah. Okay.
Approximately 10 hours later.
All right, so actually, all I said here was incorrect. We don't have to do this in this case, actually. The data is already in that form. I think I was looking at the fashion MNIST, which has that, but in this case, the MNIST dataset is just N12828, so it's in the correct shape already, so we don't have to do anything. We can just run it as it is now, and let's see how it looks in a TensorBoard. So actually, let's change the batch size to 256 just to be able to get a more images to look at in our projector, which we're gonna see soon. And also, let's now plot the embedding for each batch. If we have 60,000 training examples and we have 256 as our batch size, we're gonna have about 230 batches that we're going to train. So let's do if batch index equals 230. Then let's add the embedding. And also so this was targets before, but let's look at how our model actually predicts the labels. So let's do predictions here. We're gonna use that instead of targets. So yeah, I think I moved the class labels from here to below here, and so we're gonna see how the model predicts. We're gonna see a visualization of how the model predicts the images. Now let's train this, and let's see how it looks in TensorBoard. So it is done training, and as we can see, we have the same loss function, or the accuracy and the loss, as we had before, but just a single graph in this case, since we removed all the other batches and the learning rates. And again, we have the images here, larger images, since we have 256 as our batch size. And also we can see sort of the distribution and also the hyperparameter as we did before. So that's what we saw previously. Now what's added as the new thing is this projector thing. This projector thing is pretty cool. It has different methods that we're going to look at. Principal component analysis, which essentially just does a sort of a projection of the, in this case, 784 dimensions down to just 3, so we can kind of visualize how in this case, the model separates the different images. So we can sort of see that there are some clusters here, like the ones here are sort of close to each other, and so the zeros on this side is also quite close. The PCA, so the principal component analysis, is a little bit difficult to sort of visualize what it does. So we can use this TSNE, and I'm no expert on these methods. I don't think we have to. We can use them and sort of appreciate sort of how they visualize the images in this case, and the predictions. But the TSNE is quite a popular method, and it has sort of a few hyperparameters, the perplexity and the learning rate that you can play around with. Let's just pick perplexity 15 and sort of have the learning rate to 10. And then let's just run this for, 1,000 iterations or 2,000. And so remember that this is like how our model actually predicts the images. So we can sort of use this as a debugging purposes, I guess. We can sort of see, well, where does the model have difficulty, which does it mistake for other images, and so that can sort of contribute to what should we gather more data on, and so on. But let's see. So we can see, first of all, we have see, where are the zeros? Where are the zeros? Over here. So we can sort of see here that there's a cluster here of zeros, right? And yeah, some of them, like some 3s are close, but we can still sort of see that there's a cluster of zeros here. But this might indicate sort of some zeros are difficult, like this 0 seems to be very close. Yeah, this is actually a 0. Okay, so this one is, the correct value of this one is a 0, but I mean, I would probably say that's a 3. Yeah, all right. But so you can see, like, some might be labeled incorrectly. So that's another thing you can use this for. But let's see, what would be difficult? Perhaps 7s and 9s. Yeah, so we can maybe see here that some 7s and also 4s. Yeah, so 9, 4, and 7 seems to be quite close to each other. And sort of the 6s over here. Those seems to be quite good. All right, well, you can sort of play around with this, and you can see how the model predicts, which is very, very cool and very awesome method that TensorFlow has created. But yeah, so that's the TensorBoard introduction or overview of all the sort of methods we can use it for, and tools that it has. If you find the video useful, then please like the video. If you have any comments, then write them in the comment below. And thank you so much for watching the video.